Hey everybody, class K, we're going to talk about how to evaluate trig functions of angles larger than 90 degrees. Let me share my screen. I should write those things down. Class K. Evaluating trig functions of angles larger than 90 degrees. 90 degrees or pi over 2 radians. Before we do that, let me remind you of a couple things. Let's talk about our special triangles for just one more moment. So our special triangles, we have our 45, 45, 90 triangle. And really, you can write it any way you want. My preference when I write my 45, 45, 90 triangle is to write it, this pen's kind of dying here. Sorry, one sec. Let me grab some more pens over here. What the pens? Oh, they're right. Oh, sorry, I got my pen starting to run out of ink. You can draw this where the sides are 1, 1, and root 2, or you can draw it. I mean, there's literally an infinite number of ways you can draw it. You can draw it where the sides are. Sorry, I should make it look nicer. Like you can make it root 2, and 2. That's probably my preferred way of doing it. Or you can even go smaller. You don't have to draw them to scale. I'm just trying to draw them to scale so they look like reasonable. I'm going to use radians instead, pi over 4, and pi over 2. And you can make the sides root 2 over 2, root 2 over 2, and 1. But whenever you're drawing a 45, 45, 90 triangle or a pi over 4, pi over 4, pi over 2 triangle, these two legs have to be the same length, and the hypotenuse should always be root 2 times one of the legs. 1 times root 2 is root 2. Root 2 times root 2 is 2. Root 2 over 2 times root 2 is 1. So those are always the proportions of your 45, 45, 90 triangle. And whichever one of these triangles you use, sine of 45 degrees, it doesn't matter which one you use. It's 1 over root 2, or root 2 over 2, or root 2 over 2 over 1. All of those simplify to root 2 over 2. Same is true for cosine. That's what I like about 45 degrees, is sine and cosine are always the same. And then tangent, of course, is 1. It's 1 over 1, or root 2 over root 2, or root 2 over 2, or root 2 over 2. And then, sure, might as well be complete. Cosecant of 45 degrees. I would look at this triangle here and say it's root 2 over 1. Or, no, that's what I would just say it's root 2. And secant of 45 degrees. If sine and cosine are the same, cosecant and secant have to be the same. And cotangent of 45 degrees is also going to be 1. So I definitely, when I'm going to use this triangle a lot today. So and I'm probably going to use this version of it most of the time, and it might go back and forth. I might use radians, I might use degrees. And then the other triangle that's special, papers up here, sorry. My other special triangle is the 30, 60, 90 right triangle. And there's, in my opinion, 2 versions of this that I go back and forth between. My preferred version is probably the one where I like to draw my 30-degree angle down here, my 60-degree angle up here. And then opposite the 30-degree side is the smallest side. Opposite the right angle is the largest side. And opposite the 60-degree angle is the medium side. You can draw it that way, or you can draw it where all the sides are half as big as they were. Again, scale not really important. Angles are still the same. Or you can use radians, right? 60 degrees is pi over 3 radians. 30 degrees is pi over 6 radians. 90 degrees is pi over 2 radians. And the sides here, I'll use a different color just to be super clear. Opposite 30, I'm dividing everything by 2. So this is going to be 1/2. Opposite 90, you have 1. And opposite 60, you have root 3 over 2. Either way you want to do it, that's totally fine. And then in each of these, we see that sine of 30 degrees is equal to opposite over hypotenuse. Cosine of 30 degrees is equal to, I could go adjacent over hypotenuse and say it's root 3 over 2, or I could go adjacent over hypotenuse and say it's root 3 over 2 divided by 1, which is still root 3 over 2. And then finally, tangent of 30 degrees is opposite over adjacent, which is 1 over root 3, which is root 3 over 3. And then going the other, and then the other 3. Cosecant of 30 degrees is 2 divided by 1, which is just 2. Secant of 30 degrees is the reciprocal of root 3 over 2, which is 2 over root 3, which we should rationalize and get 2 root 3 over 3. And finally, the reciprocal of 1 over root 3 for cotangent of 30 degrees is root 3 over 1, which is just root 3. We might as well be complete here and finish our list. I should try and stay in frame, though. For the other angle, 60 degrees, which I'm going to write in radians just to be fun. Sine of pi over 3 radians, which is 60 degrees, is sine of 60 degrees, is root 3 over 2 over 1. And cosine of pi over 3 radians is going to be 1 over 2 over 1, which is just 1/2, or 1 over 2. And tangent, and also notably, right here, sine and cosine are 1/2 root 3 over 2. Here, sine and cosine are root 3 over 2 and 1/2. They switch. Tangent of pi over 3 is going to be opposite over adjacent is kind of annoying here. Root 3 over 2 over 1/2. 2's would cancel. Or you can say it's just root 3 over 1, which is root 3. And then the flips. Cosecant of pi over 3 is going to be 2 over root 3, which rationalizes as 2 root 3 over 3. Secant of pi over 3 is 2 over 1, which is 2. And cotangent of pi over 3 is 1 over root 3, which rationalizes as root 3 over 3. Great. So these are the triangles for the special angles, 30 degrees, 60 degrees, 90, not 90 is another story. 30, 60, and 45. Those are our 3 special angles, or pi over 3, pi over 6, and pi over 4. I said them out of order, but those 3 angles. So the idea now is that we're going to use those angles and these triangles along with some knowledge about the quadrants of the XY coordinate system to help us deal with some larger angles. So let's start off with, we want to find, and we'll just call this example 1. We want to find the 6 trigonometric functions. I'm going to write trig though. When I say find, or you can say evaluate, of, let's say the angle is 150 degrees. Cool. All right, so I'm going to draw it. My X, my Y, I don't really need that, but I'm right anyway. And my angle 150 degrees, I'm not going to be super precise here. Let me try and be somewhat precise with my terminal ray. There's my 150 degree angle. But now what I'm actually going to do is I'm going to drop a perpendicular to the x-axis. So if I'm above the x-axis, I'm always drawing down. If I'm below the x-axis, I'm always drawing up. So I'm going to drop a perpendicular here. I'm going to say, hey, look, I have a right triangle. And specifically, if 150 degrees is my angle here, then this reference angle, which is why we spent some time talking about reference angles, that reference angle is going to be, well, my reference angle is going to be 180 degrees minus 150 degrees, which is 30 degrees. So this angle here is 30 degrees, and this angle up here is 60 degrees. So look at that. I have a 30, 60, 90 triangle. Let me zoom in. You can all really see that. Let me refocus here. Cool. I have a 30, 60, 90 triangle, and I can label the sides. Now I'm going to label the sides, but I'm going to do one thing before I do that. I want to remind everybody that on the right side of the XY coordinate system, the X values are positive. And on the left side of the XY coordinate system, the X values are negative. And on the top half of the XY coordinate system, the Y values are positive. And on the bottom half of the XY coordinate system, the Y values are negative. So if I'm looking at this triangle, even though it's not 100% kosher to think about the sides of the triangle as being negative, I'm going to think of them that way. I'm going to think of this side here, this length in the X direction. Normally, I would say opposite of 30 is 1, opposite of 60 is root 3, and opposite of the 90 degree angle is 2. Well, now I'm going to say this is still 1 because I'm going up and Y is positive. And the hypotenuse is always going to be positive. So my hypotenuse is going to be 2. But but my base here, this leg, is going to be not √3, it's going to be negative √3. Okay, so now to find sine, well, in fact, let's actually write some more things. So I'm going to zoom back out a little bit so I have a little more room to work with. So now a little bit more. Cool. So here's what we're going to say. We know from the previous page, we know that sine, let me write this down here. Sine of 30 degrees is opposite of the hypotenuse, which is 1/2. Based on this triangle, we can say that sine of 150 degrees is also 1/2 because the opposite is 1, hypotenuse is 2. Cosine is going to be a different story. Cosine of 30 degrees is positive √3/2. We literally just did it on the previous page. But cosine of 150 degrees, not 50 degrees, 150 degrees, well, using this triangle, the adjacent side, right? So again, we're looking at this reference angle as kind of taking the place of this too big angle to be an acute angle. So the reference angle of 150 is 30 degrees, and the cosine of 30 degrees would normally be √3/2, but in this triangle drawn on the left side here, cosine of 30 degrees is going to be negative √3/2. And then finally, we know the tangent of 30 degrees is opposite over adjacent, which is 1/√3, which is √3/3. So in this triangle, tangent of 150 degrees is going to be 1/negative √3, which rationalizes as negative √3/3. And you should put the negative out in front. And then we can find all the reciprocals. I don't want to use this triangle to find the reciprocals because reciprocals, you're literally just flipping things around. So for cosecant of 150 degrees, it's going to be the reciprocal of 1/2. So it's going to be 2/1, which is just 2. Reciprocals don't change signs. So if something is positive, it stays positive. If something is negative, it stays negative. The reciprocal of cosine of 150 degrees, well, that's going to be secant of 150 degrees. And that's going to be negative 2/√3, which, yes, we rationalize as negative 2√3/3. Let's do one more. Well, one more, the last one. And then finally, cotangent of 150 degrees. Well, the reciprocal of 1/negative √3 is negative √3/1, which is just negative √3. So that's how you find the trig functions of one of these larger than 90-degree angles whose reference angle is one of our special angles. Let's do 2 more, and that'll be it. Okay, so let's look at an angle that's in quadrant 3. Quadrant 3, let's go quadrant 4, and then we'll go back to quadrant 3, actually. So let's say our angle is, and this is example 2. Let's say now we want to find / evaluate 6 trigonometric functions. There's got to be a faster way to write this. And let's do this one in radians. Let's say we have 5 pi over 3. There's also a fun fact about the reference angles of our nice special angles when they're written in radians that I will say in class, which I'll actually have you do on a handout, to be honest, but I'll say it in class as well. So 5 pi over 3, let's draw it. 5 pi over 3 is definitely bigger than 0 radians. It's definitely bigger than pi over 2 radians. It's definitely bigger than pi radians, right? Because pi is equal to 3 pi over 3. And it's actually bigger than 3 pi over 2, right? Because 5 pi over 3, let me finish before I say that. This is 0 or 2 pi, but 2 pi is equal to 6 pi over 3. So if I'm going around here between 3 pi over 3 and 6 pi over 3, 5 pi over 3, well, 5 is closer to 6 than it is to 3. So 5 pi over 3 is closer to 6 pi over 3 than it is to 3 pi over 3. So here's my, that's pretty good. Cool. There is my angle, 5 pi over 3. And here is my reference angle. My reference angle here, well, again, it's the difference between my given angle, 5 pi over 3. I guess I could label it. And the angle for the closest x-axis. And the closest x-axis is the positive x-axis. And if I've gone almost all the way around, I've gone almost all the way to 2 pi, which is 6 pi over 3. So my reference angle is going to be 2 pi minus 5 pi over 3, which is equal to, I'm multiplying 2 pi over 1 by 3 over 3 to get 6 pi over 3 minus 5 pi over 3, which is pi over 3. And just so everyone's on the same page, right, we know that pi over 3 is 60 degrees. So I'm going to end up with another 30, 60, 90 triangle. So I'm going to drop my perpendicular, but I'm dropping it to the x-axis, right? Never over to the y, always up to the x or down to the x. So there's my 30, 60, 90 triangle. Now I have to be careful here. The red angle here is the pi over 3 angle. That's my 60-degree angle, or my pi over 3. And my smaller angle over here, which I'll draw in green. Let me zoom in just so you all can see this better, hopefully. But that's a little better there. My smaller angle here, that's my pi over 6, or my 30-degree angle. So smallest angle opposite the smallest side. So let's say that this side over here is 1. And then biggest angle opposite the biggest side. So the hypotenuse, once again, is 2. And medium angle opposite medium side. So this side over here would be √3. Or, well, again, up here, y is positive. Down here, y is negative. So this part here is going to be a negative √3. This part here is a positive one, though, because, right, over here is where x is positive. Over here is where x is negative. I don't want my examples to make you think that √3 is the part that's always negative. It's just the two angles I happen to have picked so far. We're getting √3 to be the negative part. Maybe I'll do a fourth example. We'll see how the time is looking. So same idea here. I'm going to actually kind of skip the intermediate step I did last time, and I'm going to jump kind of straight to the end result here. I'm going to say the words still, but I'm not going to write them. So let's use a different color because my black pens I use too much. I'm running out of ink. So I want to find all the trig functions of 5 pi over 3. I'm going to start with sine. So sine of 5 pi over 3. Well, literally, I can just look at the triangle I've drawn, right? 5 pi over 3, sine is going to be for this angle here, even though I know it's pi over 3, it's going to be the opposite over the hypotenuse. So it's going to be negative √3 over 2. Cosine of 5 pi over 3 is going to be adjacent of hypotenuse, so positive 1 over 2. And I should point out, right, back on the first page, we saw that cosine of 60 degrees or sine of 60 degrees or pi over 3 was positive √3 over 2. And sine of pi, and cosine of pi over 3 was positive 1/2. And tangent of pi over 3 was positive √3. But tangent of 5 pi over 3 is going to be negative √3 over 1. So it's going to be negative √3. And then the reciprocals. So we have that cosecant of 5 pi over 3 is equal to the reciprocal of this. Signs don't change, so it's going to be negative 2 over √3, which rationalizes as negative 2 √3 over 3. Secant of 5 pi over 3 is going to be positive 2 over 1. And cotangent of 5 pi over 3 is going to be 1 over negative √3, which rationalizes, and we bring out the negative as negative √3 over 3. Cool. Let's do one more. Maybe two more. We'll see. Same question. So now, same deal, meaning find all of the 6 trig functions for an angle of, do I want degrees or radians? We'll do 1 more degrees, and maybe we'll hit you with 1 more radians of 225 degrees. Okay, it's bigger than 180. It's less than 270, so we know we're in quadrant 3. When you do these problems, I would like you to draw it in the quadrant so you can see what's happening here. So 225, I should find the reference angle. So again, here's 0 degrees, here's 180 degrees, 0 degrees or 360. But I know I don't care about 360 because 225 is going to be like right about there. So 225, I should draw, I'll just find it first, minus 180 is 45 degrees, and that is my reference angle. So when I draw this, and I'm going to be having a terminal ray that's like splitting the difference. Some people find the 45-degree one confusing because it's 45 degrees is the measurement from here to the x-axis. It is also the measurement from here to the y-axis, but we do not care about the y-axis. The y-axis can take a hike, to put it mildly. So there's our 225-degree angle. There is our reference angle of 45 degrees. And we're going to draw the special triangle. So I'm dropping a perpendicular. Ooh, for my last one, did I actually draw the perpendicular part, the little square part? Let's see. I would get good. Yeah, I'm dropping a perpendicular, and then I'm going to label the sides. So I don't know. I don't really know which one I like the best. I probably like the 1, 1 root 2. That's the one I'm used to drawing. So I'm going to do 1, 1 root 2, or root 2, 2, or root 2 over 2, root 2 over 2, 1. But I've forgotten something, right? And I've forgotten to zoom in 1. But I've also forgotten that this side over here, since it's on the left side, the horizontal distance should be negative. Sorry, I'm a little out of whack here. Cool. And then this side over here, since it's on the down part, right, it's below the x-axis, should also be negative. Hypotenuse, always positive. So now I'm going to find sine, cosine, etc. of 225 degrees. Again, we know that sine, cosine, tangent, cosecant, secant, cotangent of 45 degrees are all positive because that's what we've been doing. But when your angles get larger than 90 degrees, oops, sorry about that, your trig functions can have negative values. So here, sine of 225 degrees is going to equal, well, opposite of hypotenuse is negative 1 over root 2. That's the reason I don't prefer this one, because I have to rationalize it. I multiply by, let me just show the work just to make sure everyone's cool with that. And I get negative root 2 over 2. For cosine of 225, it's either going to be the same or it's going to be the same value with the opposite sign. Here it is going to be the same sign because cosine is also going to be a negative 1 over root 2, which is negative root 2 over 2. But like, for example, if my angle had been 135 degrees in quadrant 2, then sine would be positive root 2 over 2 and cosine would be negative root 2 over 2. And then we have tangent of 225 degrees, and that's equal to negative 1 over negative 1, which is positive 1. And then for the rest of them, usual process. You just flipping things over. So right, I could say, if I really wanted to think more about it, cosecant of 225 degrees is hypotenuse over opposite. So it'd be root 2 over negative 1. Right? Yeah, negative 1 here is the opposite of 45 degrees. But really what I'm doing is I'm saying it's the reciprocal of this. And then I'm just saying, oh, root 2 over negative 1 is just negative root 2. Same deal for secant. I'm just going to think of it as the reciprocal of cosine. The reciprocal of negative 1 over root 2 is root 2 over negative 1. I don't really need to write the root 2 over negative 1. You certainly can if you want to. But we know that if you divide by negative 1, it just makes the whole thing negative. So you get negative root 2. And finally, cotangent of 225 degrees. Well, it's going to be the reciprocal of tangent. So 1 over 1 is still 1. Or it's the adjacent over the opposite, which is negative 1 over negative 1. What time is it? 24 minutes. Okay, that's really kind of all there is to what we're going to do in class. We're going to look at various angles that are going to be in quadrants 1, 2, 3, or 4, right? And just in case I hadn't said it right, quadrant 1, and then we go counterclockwise, quadrant 2, quadrant 3, quadrant 4. And we're going to evaluate the trig functions of various angles that are in quadrants 1, 2, 3, or 4. And we're going to get sometimes things are going to be negative. Let me give you one more example just because I'm such a nice guy. Let's do not 150, but 120. So one more example and then we'll call it a day. So same deal, example 4, 6 trig functions of 120 degrees. Still going to draw the picture. 120 is definitely quadrant 2 because it's bigger than I was going to do. I'm going to do it in radians, which is 2 pi over 3. We know it's in quadrant 2 because it's less than pi, but it's bigger than half of pi, right? 2/3 of pi is bigger than half of pi. So it is in quadrant 2. Let's draw it. It's going to look about like this. Oops, it's kind of big, James. Oh well. So there's my 2 pi over 3. And then the reference angle, well, if this is 0 or 2 pi, and when I say or 2 pi, I'm not saying the same. I'm saying you start at 0, and then if you go one full revolution, that's when you get to 2 pi. And then this is pi. So this difference here is my reference angle, which is pi minus 2 pi over 3, which is really 3 pi over 3 minus 2 pi over 3, which is pi over 3. Or 60 degrees. So again, do the usual thing. Drop the perpendicular. I'm going to use the different version of this 30, 60, 90 triangle, or pi over 6, pi over 3, pi over 2 triangle. So there's, let me zoom in so people can see my picture better, because I do think it helps to see the picture better. So there's pi over 3, which is 60 degrees. And up here is pi over 6, which is 30 degrees. And I'm going to do the one where instead of having the hypotenuse have a length of 2, I'm going to have the hypotenuse have a length of 1. So this is a length of 1, and that's my biggest side because it's opposite the right angle. And then the small side has a value that is half of the hypotenuse length for the 30, 60, only for the 30, 60, 90 triangle, right? Not for other triangles. So the hypotenuse is always something, and the smallest side is always half of that something in the 30, 60, 90 triangle. So 1/2, and then finally, this side over here is √3 over 2, or √3 times the smaller side is the way I kind of think of it. Usually I would say it was 2, 1, and 1 times √3 is √3, but I made them smaller for fun. Oh, and I've forgotten one thing, of course. One of these two should be negative. Both of them? Just one of them. Think about which one. Okay, you thought about it. It should be this one, because we're on the left side where the x values are negative. So if you go to the left, the horizontal part is negative. If you go up or down, the vertical part is either positive or negative. All right, so now we're going to do the usual thing, find all 6 trig functions. So we're going to, and so the reason I'm doing this really is so that we see an example where we didn't have the √3 being negative. That's why I decided I should do this one again, or another example. So let's see. So for sine of 2 pi over 3, right? That's the angle we're actually taking sine of. We're just using pi over 3 as a reference. That's why it's called a reference angle, to help us figure stuff out. So sine of 2 pi over 3 is going to be positive √3 over 2. I'm not going to write divided by 1. Divided by 1 doesn't change anything. So I'll write it one time. Positive √3 over 2 divided by 1 is √3 over 2. Cosine of 2 pi over 3 is adjacent over hypotenuse. So negative 1/2 over 1, which is just negative 1/2. Now here's where things get a little bit terrible. This is why I don't love doing it this way, but it's fine. Tangent of 2 pi over 3 is going to be the opposite over the adjacent. It's going to be the √3 over 2 over the negative 1/2. First of all, I observe that overall my answer is going to be negative, because I have a positive divided by a negative. And √3 over 2 divided by 1/2 is the same as √3 over 2 times 2 over 1. The 2 divided by 2 becomes 1. So really end up with negative √3 over 1, which is just negative √3. And then I don't think about this triangle for the reciprocals. I'm just going to write them out using the knowledge I have. So cosecant of 2 pi over 3 is going to be the reciprocal of √3 over 2. So it's 2 over √3, which is 2 √3 over 3. The reciprocal of cosine of 2 pi over 3 is going to be secant of 2 pi over 3. And it's going to be 2 over negative 1, which is just negative 2. And finally, cotangent of 2 pi over 3 is going to be the reciprocal of negative √3, which is going to be 1 over negative √3, or as you should actually write it, negative √3 over 3. Great. So we're going to be doing this tomorrow. You'll probably actually see some of these same angles on the handout tomorrow. It shouldn't be too terrible. And I will see you all then. Have a lovely rest of your day. Bye.